Okay, welcome everyone. My big pleasure to introduce Arman Sarikyan from University of Edinburgh, and Arman will speak about equivariant pliability of the projective space. Thanks, Arman.
Yeah, thank you. Well, yes, I would like to tell about our joint project with Ivan Chiltsov. It was we published this article, get this result last year, and yeah, I'll explain everything, what is pliability and all this stuff during the lecture. Okay, let's start. So yeah, usually I would like always also said that Vanya and I give this talk in two different ways. So he usually speaks more about group theory and Blichfeld results, giving some historical introduction, whether my talks are usually more geometric. So I definitely recommend you to find one of his talks about this topic. Okay, let's go. So our global goal is to study G-equivariant birational geometry of P3 for all finite subgroups. I mean, P3 is very natural threefold to study. And if we just ask ourselves, what is birational geometry of P3? Well, it's impossible to answer to this question, right? Because P3 is sort of very flexible. We can do a lot of things. But if we restrict ourselves on G-equivariant maps, then we'll get something interesting, some interesting non-trivial results. So this is our goal, right? But even though if we can consider just G-equivariant birational maps from P3, still the problem still hopeless. So, however, G-equivariant Mori theory and G-equivariant Sarkisov program both suggest us to consider the following problem. Is the classification of G birational maps from P3 to other G-Mori fibered space, which is more or less doable, and this is sort of equivalent to the problem stated above, right? So, well, I mentioned what I said something like G-Mori fiber space. So let's give some definitions. So the definition of G-Mori fiber space is the following. A G-Mori fiber space is a pair of threefold Y with at most terminal singularities, and a subgroup G acting as automorphism on my Y, such that Y itself is equipped with a surjective morphism with connected fibers, such that the anti-canonical divisor is relatively ample, and every G-invariant wild divisor on Y is Q Cartier. And also we require sort of like minimality condition is that the relative equivariant Picard group is 1. So since we study P3, let's put P3 in this definition and see what we'll have. Still doesn't work. Yeah. So if the variety Y is G birational to P3, then we actually have the following three possibilities. Either Z is a rational surface and P is a G-equivariant conic bundle, or Z is P1 and we have G-invariant Delpezza fibration, or Z is a point and Y is just a rational fauna threefold with at most terminal singularities, such that the invariant class group has rank 1. So yes, nothing add more here. So we can ask ourselves a question. May it happen that P3 is the only G-Mori fiber space that G is birational, that is G birational to P3? In other words, can it happen that sort of we cannot equivariantly deform the projective three-dimensional space? And apparently the answer is yes. And in this case, P3 is said to be G-rigid. I mean, rigidity has nothing with P3 only. So in general, a variety is said to be G-rigid if that variety is the only G-Mori fiber space birational to our variety. So yes, it may happen, and we will discuss it now. actually, Ivan Chiltsov and Kostya Shramov classified all finite subgroups in PGL4 such that P3 is G-rigid. So you cannot G-equivalently, again, deform your P3. So they got the following classification: the three-dimensional projective space is G-rigid if and only if G does not, and this is a list, fix any point, leave any line invariant, leave a union of skew lines invariant, or have an orbit of length 4, or just stupidly, G is not isomorphic to A5 or S5. So all these conditions have some geometric properties, like called transitive subgroups, etc., due to Blischfeld. I don't want to go deep into this Blischfeld's result, so we just give a geometric. We just give geometric description of such groups. Okay, so yeah, I guess it's clear. So yeah, thereby we know when there are no G-Mori fiber space that are G birational to P3. So let's do the next step, and the next step is to consider non-trivial G-Mori fiber spaces. So when we have something else except of P3. However, our life experience suggests us the following intuition, that as bigger dimension is dimension of the base of Z, as more complicated life becomes by rational geometry. Hence, it is natural to give the following definition to make sort of the dimension of the base as small as it is possible. In other words, a point. So the three-dimensional projective space is G-solid if it is not G birational to a G-Mori fiber space with positive dimensional base. So this is definition of Aban and Akada, due to Aban and Akada. Again, nothing particular with P3, just any variety is said to be G-solid if there is no G-Mori fiber space that is G birational to our varieties such that it has a positive dimensional base. But we give all definitions for P3. So yeah, it's a natural condition to ask. So yeah, why it is natural? As I mentioned, because as bigger the dimension of base, as more complicated life, it's sort of also intuitively natural to ask this solidity condition. And also, what I really like about this is the following Kollár's question. So just let me remind you what is Kollár question. So let X be a Fano variety with terminal singularities and G be a finite subgroup of the automorphism group of my variety X. Let also fix a subgroup H of my group G. Then, and we also would like to suppose that the invariant rank for G and for H is always 1. Then, due to the definition, X is both G-Mori fiber space and H-Mori fiber space, right? Because the rank of class group is 1. However, there is a question of Kollár saying the following: let's assume that X is H birationally rigid, right? Does it imply that X is also G birationally rigid? We don't know. There are no examples. We sort of expect yes, because it's intuitively, it intuitively should be true, but there is no example or no proof or counterexamples for this question. So, however, it is true if we replace the word rigidity here, with solidity. If variety X is H solid, then it's obvious. Almost obviously, it's also G solid. So in some sense, this notion of being solid or solidity behaves better than rigidity. I mean, it's sort of intuition, but it's nice property of solidity as well to keep in mind. And a nice problem of Kollár, maybe some of you will solve it and provide us an example, because Vanya and I, we both don't know. Okay, let's go back to the notion of solidity. Yeah, we clearly have the implication that if P3 is G-rigid, then obviously P3 is G-solid, because I mean, if you don't have any G-Mori fiber space, then you don't have any bundle structure. But essentially, actually, the converse is almost true, indeed. So let's remind us the list of subgroups obtained by Cheltsov and Shuramov. So they said the group shouldn't fix a point. So if it is rigid, then the group shouldn't fix a point. Well, indeed, assume it fixes a point. Then we can just consider a linear projection from this point, and it will yield us a G-rational dominant map from P3 to P2, whose general fiber is P1. So in this case, the variety is not solid. Okay, the next condition in Cheltsov's and Shuramov list was existence of a line. Well, if there is a G invariant line in P3, then we can do almost the same trick. We consider the linear projection from this line in P3, right? And we get a dominant, a rational dominant map from P3 to P1, whose general fiber is P2, right? It's just projection. So the next condition was there is no fixed pair of skew lines. Well, in this case, again, we get a bundle structure. So if there is a G-invariant union of two skew lines in P3, then we can blow them up and get a G-equivariant P1 bundle over P1 cross P1. I mean, this is a classical construction. So, and also, this is something that you sort of should believe, that if G is isomorphic to A5 or S5, then P3 is not G-solid. I mean, there are several constructions that are available in the article of Kostya and Vanya, so I would rather recommend you to read them, because there are several of them, and I don't want to spend too many time on this example. Just believe me, in this case, there exists a bundle structure. So again, P3 is not G-solid. So we are left only with the case when our group G respects or leave invariant a set of 4 points in general position in P3. So yeah, as I said, so we are left to consider groups that have an orbit of length 4. And recently, Cheltsov, Diboulo, and Kishimoto studied such groups, and they obtained the following result. Suppose that your group is just stupidly big. You can see the lower bound. Yeah, it's very big. Assume your group is very big, and it has an orbit of length 4. I mean, when I say orbit, I mean orbit of points, sure. Then P3 is G-solid, and the only G-Mori fiber spaces that are G-birational to P3 are the Fan-Enriquez threefold, which is a quotient of P1 cross P1 cross P1 by an involution that fixes 8 points only. This is known to be a Fan-Enriquez threefold, and the projective space itself. So the result is absolutely clean, right? We assumed our group is big, then there are only 2 Mori fiber spaces. Hence, it's not G-solid, right? Because no conic bundle structure. So our goal was to give a complete answer to this question, right? Because this this lower bound is unreasonably big, right? And we actually, I think we successfully worked on this problem, and we got a result. So yeah, last year, Ivan and I got the following. So let G be as above. That's mean let G be any finite group that has an orbit of length 4 in P3 general position, and assume that G is not conjugated to any of the following 3 groups. These groups will be, I mean, I'll present you the matrices a bit later, but assume G is not one of these 3 concretely given groups in terms of matrices. Then P3 is G solid, and the only G-Mori fiber spaces that are G birational to P3 are, again, the Fana threefold X24 that has been discussed previously, and the projective space itself. Moreover, if G is conjugated to these groups mentioned above, then we know that P3 is not G solid. So we sort of gave the complete classification when P3 is G solid. And moreover, we almost always know we almost always know the pliability of P3. In other words, what are the G-Mori fiber space that are G birational to our given P3? It's almost always Fun and Request threefold and the projective space. And for this group, we'll have some additional models, but I will explain you a bit later. So the problem is completely resolved. So the question is, why somebody would care about this, right? Well, oh yeah, before we discuss why somebody does care about this, I would like to give you the matrices for these 3 exceptional groups. Well, this is G1, G2, and you can see these two first matrices. There are subgroups of torus acting on P3, fixing that 4 points without loss of generality. We can assume that 4 points are 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, and 0, 0, 0, 1. So these 2 groups, these 2 matrices, they are, and 3 here, they are subgroups of torus, and these 2, and this, they generate you this A4. So just very, very explicit groups. And G3, so here we have 3 torsion as a subgroup in torus, and A4 as well here, as you can see. So we have 3 exceptional groups. Let's consider counterexamples. So one can ask why they're not G solid when we have very particular construction. So first of all, assume that G is either this group or this group. That was 2 groups on the first slide. So one can consider the smooth G invariant curve C in P3 defined as follows. So as an intersection of 2 quadrics explicitly given, then these 2 quadrics defines us a G invariant linear subspace in O2, in space of all quadrics, which yields a G-rational map from P3 to P1. And yeah, and we have the following commutative diagram. So we can blow up this curve in P3 and obtain a fibration intersurfaces of degree 2, right? So it's just very, very classical birational geometry. We have a curve generated as an intersection. We blow it up, and the blow up gives us a map, a fibration intersurfaces in our case of degree 2. So hence P3 is not G solid because of this structure. So far as everything should be clear. Well, what about group number 3? Well, they actually the situation almost the same. If I click back, you will see that the defining equations for our curve are almost the same. So let me go back. You can see that I have squares here, and then boom, just cubes. I need cubes to kill this like 3 torsion that comes from torus. So in this case, we again consider the smooth G-invariant curve C defined as an intersection of 2 cubics. One can see that it is G-invariant and smooth. So again, these F1 and F2 gives us a G-invariant linear subspace, which yields a G-rational map from P3 to P1. And we again have the following diagram. We have our curve, we blow it up, we consider the vibration, and we got a map to P1 and whose fibers are surfaces of degree 3. Hence, P3 is not G-solid in this case. So if something is not G-solid, then we have clear explanation why it happens, right? So let's, before I go deep into the details of proof, etc., let's consider why actually, as I said, somebody cares about this. Well, because it's a nice notion. Solidity behaves well under considering like subgroups, and also it helps in studying of finite subgroups and conjugacy of them for Cremona group or birational automorphism of P3. So as an example, let's consider this group. Let's consider this group, yeah, as a subgroup in PGL4 generated by these 5 given matrices. So these matrices represent you this mu3 cube subgroups of torus, and these groups are these matrices generate you S4. One can easily see that these groups satisfy our condition. It has the orbit of length 4, the tetrahedron, the vertices of tetrahedron. So we see that as groups, G is isomorphic to that exceptional group G3, but by our result, this group is G-solid. However, G3 is not G-solid. And just a reminder, G3 generated almost by the same matrices, except of minus here, I mean here, and minus here. So we just erase these 2 minuses. We got isomorphic group, but non-conjugated actually in PGL4. And apparently, by erasing just 2 minuses, we completely changed the equivariant birational geometry of P3 with respect to 2 similar groups. So hence, we have 2 isomorphic groups that are not conjugated in Cremona or in group birational automorphism of P2. Another example that I actually like when you came up with this example. So let's consider the following group. This is mu2 square semi-direct by A4, again, as a subgroup in PGL4, generated by the following matrices. And let's consider this quadric, Fermat quadric in P3. Then one can easily see that this quadric is G-invariant. I mean, indeed, these minuses do not change anything because we have squares, and these 2 matrices just permute coordinates. So quadric still quadric. So then the quadric is G-invariant, and which is, yeah, hence it gives us a faithful action of the group G on this product of quadric and P1. And this action actually induces an embedding of G into Cremona, some non-trivial embedding probably. And we know by our result that this group is actually G-solid, right? According to our theorem. However, we just we alternatively constructed a variety that has a conic bundle structure, that has a quadric bundle structure over P1, by definition, almost, this group is not G-solid. Hence, these groups are not conjugated in P3. Well, so what else do we know from our result? I told you that if G is not one of these three exceptional groups, then we know all possible G-Mori fiber spaces. In other words, we know all plausibility of G equivariant plausibility with respect to the groups. However, if we consider this exceptional group G3, one of these exceptional groups, we can actually prove that there are not two, but three models, right? So if we consider G birational maps, G3 birational maps, then we only have, again, our P3, we only have X24, and we only have this cubic fibration that I presented above. So nothing else, only three models. Unfortunately, we don't know the answer for that two remaining groups, G1 and G2, two exceptional groups. However, we expect the similar result. And so Ivan Chiltsov, Igor Krylov, and I, we work on the similar result for these two exceptional groups, but the birational geometry there is much more complicated because these groups are small. They're smaller than this G3. So yeah, in this exceptional case, we know all G-Mori fiber spaces as well. Okay, so let's understand a birational map from P3 to X24. I mean, I mentioned it several times, but I never described it. So let's talk about it. So by assumption, there is a G-orbit in P3 of length 4. This is our assumption for the rest of my talk. So we denote these points as P1, P2, P3. As I said, we can, without loss of generality, we may assume that they are the vertices of the coordinate tetrahedron. So, I mean, if you have a tetrahedron, you definitely want to consider it, right? So let's, for every I and J, let Lij be the line in P3 that passes through Pi and Pg. So it's basically the edge of my tetrahedron, the edges. And let M be the linear system consisting of all sextic surfaces in P3 that are singular along this line in my tetrahedron, every edge of my tetrahedron. Then we actually can explicitly give you the surfaces in M. They're given by this horrible equation. So you can check it by computing Jacobian that they are indeed singular along every line. And what is more remarkable that this is 13-dimensional, this is 13-dimensional linear space, linear system, So that linear system hence gives a G-rational map from P3 to P13, and one can prove that this phi is undefined exactly in these lines, in the edges of my tetrahedron, and the image is exactly X24. I would definitely recommend you for more details, to go to Vanya's article on Vanya Dibulan Kishimoto on when G-toric Fana threefolds are solid. They explicitly gives you these birational maps in terms of links, flops, etc. So very nice and precise description. So for our purpose, we just need to know that actually there is a G equivariant map from my P3 to X24, whose base locus is exactly this tetrahedron. I mean, the edges. Well, so let's go and discuss a little bit in more details our proof. So we keep our previous notation. We study these subgroups that leave invariant a set of 4 points. Notice that all such subgroups fit in the following exact sequence, where T is a finite subgroup of the torus acting diagonally, as you have seen in matrices above, right? We have these diagonal matrices, and our gamma is either A4 or S4. So it's just permutation of this set of 4 points. I would like to mention that Blishfeld, in his work on classification of finite subgroups in PGL4, he left these groups without any details provided. Like he said, there is a family of groups that leave invariant a set of 4 points. That's it. So we actually studied a little bit the structure of such groups. For example, there's a nice lemma that if G is as above, then one has the following 3 possibilities: that T is either mu n cube, or it is mu n squared times mu n over 2, or if n is divisible by 4, then T is the following. And we got some nice results. For example, if n is odd, then it is always mu cube, and G is always a semi-direct product of T and gamma, and moreover, there are only 2 semi-direct products. So we sort of got some partial classification results of such subgroups that we used actually to study the equivariant geometry. So yeah, this some information about such groups. And let's discuss about the strategy of the proof. So we heavily use these linear systems to study pliability, especially Noether-Fano inequality. So the Noether-Fano inequality is just a magical tool, if you're not familiar with. It's just a magical tool that in our particular case yields that in order to prove that the main, theorem, we need to show only 2 things. We need to prove that for any mobile G linear system M on P3, the non-canonical locus of it is either the edges of tetrahedron or the vertices with multiplicity greater than 2. Why? Because the edges gives you the map to X24. We know that such map does exist. So we are doomed to have this non-canonical linear system. Moreover, that non-canonical linear system would be exactly that linear system of sextics, singular along this edges of tetrahedron, or the vertices, right? Vertices are also invariant, and vertices correspond to Cremona transformation, just a usual Cremona involution. And we also, I forgot to mention, what is this lambda? This lambda is such number that, that canonical class plus lambda m is Q rational to 0 for some lambda. And also the same situation for X24. The next step is we studied that. I mean, what this first case says us, right? It says that the only variety where we can go from our P3 is either P3 itself via Cremona transformation or to X24. So now we are in X24 and we need to study its birational geometry and to prove that there are no other models, or maybe there are some models, but like there are no conic bundles, right? So in that case, we actually prove that the only non-canonical locus for such pair is one of two orbits of 4 singular points in X24, and one orbit will give you a map to P3, and another orbit will give you a map to another P3, which are connected by Cremona transformation. So we have sort of like this love triangle. We have P3 goes to X24, and from this X24 we can go to another copy of P3, and they are connected by Cremona transformation. Cremona involution. Yeah. So let me provide you a sketch of proof for the case of P3 and for sort of big groups. In general, the whole proof is quite technical. You need to consider curves of some invariant curves. You study their geometry on P3, on X24. It's quite messy, but there is a nice part when your group is relatively big, for where, I mean, by big, I mean n equals greater or equal 3. This n is the torsion, the biggest torsion in your the biggest torsion in T, right, in notation above. So let's discuss this sketch of the proof for P3. So we show that there are no G-invariant curves of degree less or equal 15, except of the edges of tetrahedron. Hence, we do not have any extra one-dimensional non-canonical centers. Like automatically, we kill these curves for very cheap price. So we need to consider points as possible centers of non-canonical singularities, and so all orbits of points are classified, and we have the following. So these orbits, they either contained on the edges of tetrahedron, and in this case, these orbits cannot be the center of non-canonical singularities due to Puchlikov's 4n square inequality, a very famous result. I'll provide you some details and proof later. Or if you consider a general orbit, then that general orbit cannot be the center of non-canonical singularities due to the Nadal vanishing and this multiplier ideal shift technique. So yes, this is our strategy, how we got rid of these all centers. And let's actually discuss a bit in more details these two cases, how we actually prove that these points are not centers of non-canonical singularities, because usually when you study non-canonical singularities, points are the most interesting cases. Okay, so theorem. It's not theorem, it's actually like a lemma at most, but sorry. So let's P be a point that is contained on our tetrahedron, on our edges of tetrahedron, and we assume that P is not one of the vertices, right? Because vertices, as I said, gives us vertices give us a map to another P3. So then the orbit of our group of our point P cannot be the center of non-canonical singularities. This is quite a classical technique and classical result due to classical result of Puchlikov. Okay, let's discuss it. So assume the converse, and assume that there are k points on an edge. Hence, the whole orbit contains 6 times k points. Consider the following linear system of cubic that pass through our tetrahedron. We can explicitly provide you the generators of this linear system. Here they are. And one can check that its base locus is exactly this tetrahedron, the edges of it. So then by Puklikov's 4n square inequality, we know then if a point was a center of non-canonical singularities, that actually the multiplicity of intersection of two general members from our linear system, lambda m, has multiplicity greater than 4 strictly. Okay, let's consider this intersection of two general members from lambda m. So we know that they must contain our tetrahedron with some multiplicity and some effective curve delta. Hence, by Puklikov's 4n square inequality, we have that multiplicity of a point P in this delta is greater than this number. So yeah, let me repeat it. Then for a general surface from this linear, then we take a general surface from this linear system and we intersect, we just intersect and we get a system of inequalities that doesn't have a solution. So a contradiction, right? The contradiction was that we assumed that P was a center of non-canonical singularities. Okay, as I promised, I will also provide you a proof of the fact that P, a general orbit of points, cannot be a center of non-canonical singularities as well. So without loss of generality, now we can assume that P is not contained in my tetrahedron, right? Then the orbit cannot be the center of non-canonical singularities. This is due to another fundamental result, Nidal's vanishing, and we also used Court inequality, so quite nice proof. That's why I really wanted to provide it. So we assume that the pair again is not canonical in our point P. Hence, I mean some extra words should be said, but in this setting we can actually show that 3/2 minus epsilon times our linear system is not log canonical at P. I mean, this is a bit non-trivial, but for more details, go to our our article. So suppose that we actually, I mean, once we multiply by number, we got a non-canonical, we got a not log canonical pair, right? We probably got a new non-log canonical center, which can be a curve, for example. Let's prove that we will not obtain a curve. So suppose that the pair, the new pair, is not log canonical in a curve, in some curve C. Then we just intersect two general members from our new linear system, and we get this curve C, and plus some delta, and this m, this multiplicity, is greater than 4 by Cortis inequality. So thereby we can consider a hyperplane section. We can consider a hyperplane section for this equation, and we will see that the degree of this curve C is strictly less than 9. So due to our classification result above, C, there are no curves of degree less than 15, G-invariant curves of degree less than 15. Oops, there is a question. Yeah, thank you. That is not a union of the edges of tetrahedron. So contradiction, and we supposed that that our and we suppose that our point is not contained in tetrahedron. So is this another question? Sorry. Yes, this book. So thank you very much. So yeah, hence we prove that P is not contained in a new log canonical center that is a curve. So hence P is isolated. Sorry. Okay. We know that our point P is isolated center of non-log canonical singularities. Let Y be the locus of non-log canonical singularities. We denote as I, this curly I, the multiplier ideal sheaf. Then by the Nadal vanishing theorem, we obtain the following. it says that this cohomology vanishes. So we can consider the following exact sequence, the classical exact sequence. I mean, I would like to notice that I is actually an ideal sheaf of Y. So the ideal sheaf of Y. I mean, some details should be said, but it's true. So we consider the following exact sequence. We tensored it by 2, and due to Nadel's vanishing, this exact sequence yields this rejection map from 10-dimensional vector space to this vector space. However, we notice that what is Y? Y at least contains the orbit of my point P, and due to our classification results, that this orbit has length at least 16, because we assumed in very beginning that n is greater or equal than 3. So we have a surjection map from 10-dimensional vector space to at least 16-dimensional. I mean, that's contradiction. So this is how we got rid of points that are outside of tetrahedron. So everything is nice and cool, and I would say even obvious, in the case when n is greater or equal 3. As I said, because for the reason that our group is quite big. However, when the group is small, the proof becomes much more complicated, like very complicated. I would say actually n equals 2 is the most important and the most difficult case in our article. So the reason is that there are actually a lot, infinitely many, of orbits of points of small length. So you can't just use this Nidal vanishing, because we'll have points of orbit whose orbits are less than 10, yeah. And orbits of curves of small degree. This is another problem, right? Because in previous case, we just basically didn't have any curves of small degree. We didn't even consider them as possible centers of non-canonical singularities. In the case of when n equals 2, we have a lot of them. Yeah, for example, we can consider the smallest possible group that respects this like set of 4 points. Here's our these generators of this group. This group is isomorphic to mu2 square semi-direct to A4, and we know particular its gap ID, so everything is available. Yeah, just in case, in our article we provided all gap IDs for everything. As far as I remember, Tim Dakshitsa wrote us an incredible script that just you just put in that script the generators of the matrix, you press the enter, and it gives you the gap ID. We were shocked a bit. So yeah, if we consider this the smallest possible group that is actually solid, then here's like its orbit. It has 3 orbits of length 4, so sort of there are 3 tetrahedrons, and just infinitely many orbits of length 24, infinitely many, yeah, just this horrible mess. So proof should be more delicate here. And as for fun, yeah, just a fun example of one-dimensional orbits. Apparently, it was very interesting and unexpected for us. There are infinitely many orbits of 4 smooth twisted cubics in P3 with respect to the group provided with that group. More precisely, these 4 twisted cubics are the orbits of curves given by this horrible system. Moreover, you can see a parameter S here, so it's actually like one-dimensional family of these twisted cubic curves. Sometimes they intersect, sometimes they do not, but luckily they do not affect them. Actually, they give nothing. They cannot be centers of non-canonical singularity, of non-canonical singularities, due to some more delicate reasons. Yeah, I guess this is it. Vanya? I mean, you can ask me any questions since Vanya left us.
Thank you,
Oh,
Arman.
welcome back. Yeah.
Okay, let's thank the speaker in Zoom. Okay, thank you for excellent talk. A bit fast, but it's okay, a bit short. So any questions to Arman? Okay, so I have a question. If you consider instead of geometric group action, if you consider arithmetic group action and consider Severi-Brouwer varieties of dimension 3 with action of Galois group, can you repeat basically this?
Well,
Can you repeat the same approach, for example, to study pliability of Severi-Brouwer varieties over some fields with prescribed Galois group action?
Well, I guess we discussed it. We sometimes discuss it with you. Well, I guess. I mean, probably.
No, like
yes.
similar what Tripalin did, for example.
Yeah. Should be doable. I mean, I like as we discussed with you. I think it should be doable. But Tripalin used. I discussed it with Andrei Tripalin. He used some abstraction in Amitsur group in Severi-Brouwer that basically do not work here. So he had arithmetic abstractions because 3 is not 4 and 3 is a prime number, sort of like that.
Okay.
So as far as I remember his ideas.
But I think it would be interesting just at least to find examples of say Severi-Brouwer varieties which are rigid or solid. So, for example, every Severi-Brouwer variety of dimension 2 without points are solid by Tripalin and not rigid because it has two non-isomorphic models, which both Severi-Brouwer. Yeah, but in this case, I don't know. We don't have even a single examples. Yeah.
Well, frankly speaking, I don't have much motivation. I mean, like I can't see why one should study solidity, which is quite geometric condition in arithmetic case.
No, it's because it's the same. It's solidity of a non-closed field. It actually has even older history than geometric action.
Yeah, I mean everything came from arithmetic. Yeah, I understand.
Okay, good. Any other question to Arman? Okay, if no, let's thank Arman again. Thank you.
Yeah. Good.
Okay, let me stop recording.